Question number 2. A metal bar whose temperature is 20 degrees Celsius, right? Yeah. Is placed in boiling water. Yeah. All right. Here, we use the Newton's cooling law, right? Yeah. So we know we should use Newton's cooling law. All right. The question is how to use it. Yeah. All right. First, we have a metal bar. Yeah, but the boiling water. Yeah. So let me draw some simple diagram. Yeah. Boiling water. Okay. All right. Then metal bar. Yeah. Putting this boiling water and we treat. So the boiling water part is the environment. Environment with the temperature T sub A, right? Yeah. And the metal bar temperature T, capital T of time T. Yeah. And then by the Newton's cooling law, yeah, we set up ODE, the modeling part. Yeah, we know the rate of change dt over little d little t. Yeah, yeah. Here, the temperature of the metal bar is lower than the boiling water. Yeah, from 20 degrees going up. Yeah. Closer and closer to 100 degrees Celsius. Yeah. All right. So here we like to, use when we apply the Newton's cooling law. Yeah. So we may write it slightly different what we did in our examples in the class. Yeah. But here, actually essentially the same, but we write, so we need a constant K. Yeah. Then we use the boiling water temperature T sub A minus that T. Okay, yeah, because in this way, we know this is a positive, right? Greater than 0. Yeah. Then, the temperature going up, so the derivative of the temperature also positive, right? Yeah. So here you can see in this way, we can make this constant K also positive. Yeah. All right. So then you solve this equation for T. That's pretty easy, right? Yeah. All right. So when you solve this equation, so I think you can write, but when you write, yeah, so here, I do not write the complete formula right here, but there is a constant C part, right? Yeah. So here there is one term here. Yeah. All right. Yeah. So, and e to the kt. Yeah. All right. Then you can determine this C by the initial value, right? Yeah. Because T of 0 equals 20 degrees C. Yeah. So you can determine this capital C. After that, yeah, so you have another temperature, you can determine this K. Okay, all right, yeah. At 1 minute, right? Yeah, 1 minute. So your little t, you use the minute as the time unit. No, you do not use hour. Yeah. Yeah. Actually here, some of you, if you want to ask, how do you know you should use the time unit, hour or minute, for your convenience, because when you actually you can both use hour or minute, but if you use hour, its corresponding K is different. If you use the minute, then you just use a different K. But the product actually the same, K times T. After you change the unit from minute to hour, from hour to minute, the whole exponent number is the same. So you just pick one that you feel convenient. So here we feel, the minute way is more convenient. So you use that way. So T of 1 equals 51.5, right? So you can find that little K. All right. Then the last step, pretty obvious, right? So last step, you need to get a little t1 equals 99.9 degrees Celsius, okay? To find this little t1. So that's pretty easy. All right, so that is the question number 2.